So, how do we use this new knowledge of an a right triangle and understanding of how to put vectors together and to define a resultant force to be able to define what we call the rectangular components of a force? Because this will make things a lot easier in the future for us as we get into more complex systems. And so the rectangular components, this is just talking about um, our perpendicular components, also known as our x and y components of our force, so that we understand how that force is acting in the x direction and in the y direction. So we're going to use our concept that we just talked about of a right triangle. So we have a right triangle here, just like we do here. And we talked about, say, this angle, theta. So we're defining this angle, theta. And we had our adjacent side here, our opposite side here, and our hypotenuse, which also is f of x. And then this opposite here is f of y. And our hypotenuse is our force. So looking at those sides, that's how that's defined. So using what we know with ka, toa, we can define the rectangular components, which are fx and fy, by using this relationship. So how do we do that? Let's start with we have the sine of our angle theta is equal to the opposite, which is fy, over our hypotenuse, which is f. We have our cosine of theta is equal to our fx, which is our adjacent, over our hypotenuse. So if we need fx and fy, we can solve these for that. So fy is equal to f sine of theta, and fx is equal to f cosine of theta. So this is how we define the magnitude of our rectangular components. Now, how do we know that vectors have magnitude and direction, so we would be defining these as using our unit vector, which we previously talked about. So our force vector is going to look like f cosine of theta in the I hat direction plus f sine of theta in the j hat direction. This is allowing us to define the magnitude and direction of each of these components. So we have magnitude, direction, magnitude, and direction of our force vector. All right, so knowing what we know now about how to add and put together the forces in a system, if there's 2, 3, or however many, to get a resultant force, we can either use the parallelogram law, or maybe we can do something cool with this new rectangular, or what we call Cartesian notation, to be able to simplify this and define our systems using the Cartesian coordinates. So let's look at this. We have our X and Y world. And we're going to add some forces in here. So we'll draw them as green. I have force 1. I have force 2, and say I have another force 3 acting on my system. Okay, let's try and figure out how we can do this without that complex parallelogram law. We can do something where we define each of these in their Cartesian form. So we can say F1 vector is equal to F1x, or the magnitude, the x component, the magnitude of the x component and its direction I hat, plus F1y and its direction j hat. And we can define 2 the same way. So we have F2x I hat plus F2y j hat, and F3 F3x I hat plus F3y j hat. So we have each component or chunk or piece of each of these force components defined in our x directions and our y directions. So this can make it a lot easier, because then our resultant is now going to be, our resultant vector is equal to F1, F2 plus F3, which we've done before. We did that with the parallelogram law. But now, instead of doing the parallelogram law and using the law of sines and cosines, we can simply add components, because these are already predefined as all in the I direction and all in the j direction. So I can do this. I can define my resultant as F1x plus F2x plus F3x in the I hat direction, plus F1y plus F2y plus F3y in the j hat direction. So this can really simplify our ability to find our force resultant, which we can then just define as the x component of our resultant in the I direction plus the or the y component of our force resultant in the j direction. So using Cartesian coordinates and definitions of our vectors can really simplify things for us. So what this really means, this means therefore F Rx is equal to the sum of the forces in our x direction, and Fry is equal to the sum of the forces in the y direction. This is going to be a resounding theme in everything that we do in statics. You can also then use this information to define the magnitude, which we define like this, if you want, is equal to that direction, or the distance formula, Frx squared plus Fry squared, which is the same as the law of cosines, but we have a orthogonal, or we have a right triangle in there, so that last term just falls off. And then the angle of Fr with respect to the x-axis is going to be the arctangent of Frx over Fry. And this would be using our SOHCAHTOA. So we're going to end up with a resultant vector. It's probably something like this. And so this would be defining the angle with respect to x. And so then we have our x component here, our y component here, and you can define that angle or find that angle by taking the opposite or the TOA, the arctangent of FRY over FRX.